The red spheres represent positive current, which is in the opposite direction of electron current. In a bipolar junction transistor, a small current flowing into the middle terminal controls a much larger current through the transistor's two other terminals. Bipolar transistors are one of the two main types of transistors. In this other type of transistor, the middle terminal does not have any current passing through it during steady-state conditions. Here, it's the voltage of the middle terminal that controls the current through the other two terminals. This is called a field effect transistor. There are two main types of field effect transistors and two main types of bipolar transistors. We can tell them apart by whether the arrow is pointing toward or away from the middle terminal. In bipolar transistors, the positive current flows in the direction of the arrow. The red spheres symbolize the positive current. This is a NPN bipolar transistor. This is a PNP bipolar transistor. Here, it's the positive current flowing out of the middle terminal that controls the transistor. Let's now focus on field effect transistors. The two main types of field effect transistors are two different types of metal oxide semiconductor field effect transistors, abbreviated MOSFETs. This is an N-channel MOSFET. As always, the red spheres represent the direction of positive current. Here, a decrease in the voltage on the middle terminal will cause a decrease in current. An increase in the voltage on the middle terminal will cause an increase in current. This relationship is reversed for a P-channel MOSFET. In both cases, the voltage that controls the transistor is the voltage between the terminals that we call the gate and the source. In the N-channel example, the source is shown at the bottom. In the P-channel example, the source is shown at the top. In both cases, the voltage difference between the gate and the source has to exceed a certain threshold voltage before it starts having any effect. Since it's the voltage between the gate and the source that controls the transistor, the current will not increase much if we increase the voltage at the drain. But if we reduce the drain voltage, we'll eventually reach a point where the current will significantly decrease. The behavior of bipolar transistors is different than field effect transistors, and the terminals have different names. Here, when the current is flowing, the difference between the base voltage and the emitter voltage stays at about 0.7 volts, and the collector current is the base current multiplied by a large constant number. Suppose we add another resistor as shown. A change in the current through this resistor causes a change in the voltage drop across it. Here, the collector voltage is 0.3 volts above the emitter voltage. If the base current is increased further, the collector voltage is unable to go any lower. Here, all the currents are staying constant. Here, the bipolar transistor is behaving like a switch in the on position. But it's not an ideal switch because there is a 0.3 volt drop across it. On the other hand, when a MOSFET behaves like a switch in the on position, it's not an ideal switch because it behaves like a resistor with a small resistance value. A MOSFET is unable to block in the reverse direction because there is a diode inherently built into its body. Also inherently built into each MOSFET are capacitors between each of the terminals. Although it's not shown in this video, these capacitors need to charge and discharge, and there is therefore a brief momentary current through the gate terminal when the gate voltage changes.